Hello everyone, here I am introducing our work, Learning Occupancy for Monocular 3D Object Detection. Monocular 3D detection is a challenging task due to the lack of accurate 3D information. Existing approaches typically rely on geometry constraints and dense depth estimates to facilitate the learning, but often fail to fully exploit the benefits of three-dimensional feature extraction in frustum and 3D space. In this paper, we propose \text OccupancyM3D, a method of learning occupancy for monocular 3D detection. It directly learns occupancy in frustum and 3D space, leading to more discriminative and informative 3D features and representations. Specifically, by using synchronized raw sparse LiDAR point clouds, we define the space status and generate voxel-based occupancy labels. We formulate occupancy prediction as a simple classification problem and design associated occupancy losses. Resulting occupancy estimates are employed to enhance original frustum/3D features. We present the network overview of our method. First, a single RGB image is fed into the DLA34 backbone network to extract features. Then, we use these features to produce categorical depth distributions, which lifts 2D features to frustum space. After that, we employ the depth predictions and backbone features to generate frustum features. They are used for learning occupancy in frustum space, and then are transformed to voxelized 3D features using grid sampling. Such voxelized 3D features are employed to study occupancy in 3D space. Occupancy learning in both frustum and 3D spaces can produce reasonable occupancy estimates that enhance the original features. The final enhanced voxelized 3D features are passed to the detection module to obtain final 3D detection results. At the training stage, occupancy estimates are supervised by the generated occupancy labels in frustum and 3D space, respectively, using the proposed occupancy losses. We employ depth predictions and backbone features to generate frustum features. We employ depth predictions and backbone features to generate frustum features. They are used for learning occupancy in frustum space, and then are transformed to voxelized 3D features using grid sampling. Such voxelized 3D features are employed to study occupancy in 3D space. Occupancy learning in both frustum and 3D spaces can produce reasonable occupancy estimates that enhance the original features. We use synchronized raw sparse LiDAR points to generate occupancy labels by using 3-space, free, occupied, unknown. Occupancy has some similarities with 2D depth map, especially the frustum occupancy. They both can represent object geometry surface in the space. However, depth map is two-dimensional, while occupancy is three-dimensional. Occupancy is beyond the depth and can base on it. It is able to express dense features of objects, but not only the surface. This is the comparison in OnKitty test set. The red refers to the highest result and blue is the second highest result. Our method achieves state-of-the-art results. This is the comparison in the Waymo dataset. The red refers to the highest result and this is the comparison in the Waymo dataset. The red refers to the highest result and blue is the second highest result. Our method also achieves state-of-the-art results. To investigate the impact of each component in our method, we conduct detailed ablation studies. Following the common practice in previous works, all ablation studies are evaluated in the validation set on the CAR category. This is the main ablation of our method, which demonstrates the effectiveness of each component in our overall method. Also, on OnKitty pedestrian and cyclist, our method achieves state-of-the-art results. We also provide some qualitative results. We can see the occupancy estimates and 3D detection results. Thank you.